All right, well, good afternoon, everyone. Happy Wednesday, and welcome to our talk on networks in a nutshell. This is going to be presented by Sophia Serrano. She is a PhD candidate at UW, getting her degree or doctorate in computer science and engineering. Very excited that you guys are all going to be here, and I'll turn it over to Sophia to kick us off.
Sweet. Thanks, Caitlin. Yeah, as Caitlin said, I'm a PhD candidate in CSE at the University of Washington. And so when I was first sort of talking with Caitlin about what the idea for this sort of seminar would be, it sounds like the sort of theme of the seminar this quarter is sort of like machine learning fundamentals, building up to some more current uses of machine learning that have been in the news recently. And so I was thinking about like machine learning, there's so much to cover. What do I cover? Neural networks feel like probably like if you're gonna know like even just a little bit of machine learning, this is probably the area that you want to put at the stage. So first of all, neural networks, like maybe you've heard that term before, maybe you haven't. You have for sure seen these before. Even if you haven't heard them called by that name, you have absolutely encountered neural networks. So in like the past, did DALL-E come out in the past year, a little bit before that? Recent. So if you've seen any of the model outputs from like DALL-E or ChatGPT or before that GPT-3, any of these models developed by OpenAI, for example. OpenAI are not the only people developing these models by any means, but there's tend to be some of the most famous ones. The bread and butter of what underlies all of these models are neural networks. These are essentially very large neural networks that have been trained, but neural networks have actually been around for longer than that. They really sort of took off in, I would say, the mid 2000s was when people started to really think like, actually, no, these might actually work. They've been an idea for longer than that. And interestingly, the building blocks of actually like what makes these models work, how these models are trained, has actually stayed pretty consistent over time. So I'm going to be talking today about what I think really the two main components that unify these neural networks are. The first is gradient descent. If you don't know what that is, that's totally fine. That's my job to tell you. The second would be loss functions. So we're going to spend today talking about those two ideas. And then at the very end, I'm going to sort of show how those two concepts are combined in order to structure and train a neural network. And then I'll close with like a few more words about what that implies about how these kinds of models use data, so on. Any questions right out the gate, I guess? Okay. So as we're getting into gradient descent, I want to offer kind of like a motivating example. Suppose that I'm like, hey, we're going to go on a hike. And you're like, hey, Sophia, it's already 9 p.m. And I'm like, no, we're going today. We're going today. And you're like, okay, well, at the very least, we should pack like flashlights. And I don't know what food do we bring. And I'm like, no flashlights. It's fine. We're leaving now. It'll be great. And so we arrive at this river canyon. And I'm like, okay. So again, I know it's late. I know it's dark. I know we can't see, but we are going to finish this hike. And again, you're questioning like, why did I come with this person? That's out of scope for this. You came with me. Also, I should maybe mention, in this case, the river in this diagram is actually solid. We're going hiking in Minnesota in like the middle of winter. So you might be worried about like anything from like poison ivy to bears. Those are out of scope for this scenario. We're going to start at sort of like some point further up in this canyon. And I've decided that like this hike is going to finish at the lowest point of this river canyon. You're like, okay, I would like to go home. So it's in my interest to like just finish the hike. So we start out and let's suppose okay, like now we need to actually come up with a strategy, right? To reach the bottom of this river canyon, even though it is pitch black out. Now, suppose that we just start here, right? Like suppose that that's our starting point. Well, it's pitch black. How are we going to make our way down to the bottom? Well, we are going to basically do a process that we're going to repeat a bunch of times, and that is going to be to bend down, feel the ground around us locally, like around where we're standing, find the steepest direction up, and take a baby step in the opposite direction. Given this contour plot, I think the steepest direction up is this way, if I'm reading this plot correctly. So suppose that that's what we feel by like feeling the ground around us. Okay, great. So now we're going to take a step in the opposite direction, just a tiny little baby step in the opposite direction. Now, what are we going to do? We're going to repeat that same process. And this time we find that that direction has like slightly changed, right? The steepest direction is now a little bit different. So we're going to take a baby step in that direction. Okay, well, we can keep doing this and keep doing this until eventually we will reach the bottom, right? Like either we will find that there is actually no further down we can go, or we still have some progress that we can make towards getting further down. Okay. So first of all, does this make sense? I know like this, again, like maybe a slightly unrealistic hiking scenario, preferably like kind of unrealistic. Okay, so now that we've kind of set out our basic strategy here, I want to introduce like the idea of coordinates, right? So I don't think this is anything too radical to do here. We're already pretty familiar with the concepts of like east to west and like north to south, right? Like I know like, yes, technically, like the earth is round and all of that, but like in this case, we're looking at a small cross section of the earth. So we're going to pretend it's a flat plane, right? So we have north to south and east to west, and we can just like overlay some coordinates on this two-dimensional space that basically represents like this bird's eye view of this canyon, right? So I'm going to go ahead and just like place some axes there. Like, I could center the axes somewhere else, but just to give us the idea of like overlaying a coordinate space onto this. Suppose that like this point that we're now at represent, I don't know, like 4, 4 or something. I'm absolutely just making these coordinates up. But suppose that we have our current point. It turns out that we can also describe this sort of direction that we find in a separate set of coordinates. So essentially by measuring like, okay, proportionally, how far south would I step and how far, I guess this is east. I know my east and west. How far east would I step and sort of blocking that proportion into place? Let's say that this is like 1 and this is like 3.5 here. I can also express this direction in terms of like coordinates, right? So basically, if I add like some tiny little multiple of this, right? Like just multiply both of these numbers by something very small and positive, and then subtract that from this, then I get basically my next point. And I can keep doing this and like keep getting these direction vectors until I reach the bottom. Okay. So now that I've set up this motivating example, right, we can actually fade out this idea of like having a map and having a north, south, east, west. Like this concept of trying to find the lowest point is actually something that is far more abstract and general than just this hiking example that I've laid out. So the reason why I laid out like all of these terrible hiking ideas of like, we have no idea about this global space that we're in is precisely because we've just created a method basically for us to, even if we don't know the global sort of characteristics of the landscape that we're in, we can still find the bottom. And that will actually end up being a really powerful idea when we start thinking about the training of neural networks. So just to walk through, just to like make sure that we're all on the same page with how this procedure works. If I were to walk through another step of this procedure, but this time in coordinate space, right? So not just visually. Basically our new point, given this current point that we're at, and this, what I'm going to call a gradient vector, we'll get to that. But this direction vector that tells us the steepest direction from where we are right now, our new point is going to be our current point minus something very small times the direction that we have, right? So essentially, let's say like I picked like 0.1 or something. This was just because I didn't want to type out a bunch of tiny decimals. In practice, we often choose something much, much smaller than this. But to give you an idea, our new point would end up being like, we're going to move a little bit left. So we have like 3.9 now instead of 4, and like a little bit further up than that. So we're now at like 4.35 instead of 4, right? And so even though we no longer have like a visual of the map that we're referencing, provided we have some sort of like outside help that will keep feeding us these direction vectors for each new point that we feed it, we're still able to find the lowest point. So that's like a 2-dimensional version of coordinate descent or of gradient descent. But actually, this idea, not to make things even more general once again, but to make things even more general once again, there's no reason why this idea has to be in 2 dimensions. Yeah.
This gradient will happen.
Yeah, it is. So good question. So I am trying today to like keep the calculus out of it. Like the calculus is our friend and it gives us things. But in order to understand this talk, like basically the view of calculus that we're going to have is like a black box where like, provided we meet certain conditions, it does our work for us. Good question. But yes, that is exactly where the gradient is from. Okay, so sort of building off of that, right? Like, okay, the reason I started us with 2 dimensions is because it's way easier for us to like visualize moving around in this 2-dimensional plane, right? With kind of like a bird's eye view of this landscape. But this idea of like, we have an ordered set of numbers and another ordered set of numbers that represents a direction we can move from each of those coordinates, there's no reason why that has to be limited to 2 dimensions. At this point, it gets real hard for us to visualize, so we won't try that. But the same exact idea here of like having some points, right? Or like, sorry, this would represent a single point that is basically like an n-dimensional ordered set of numbers. And then what we do to like find the point that corresponds to like the lowest altitude in our higher dimensional space is just iteratively keep subtracting very small multiples of the corresponding gradients. Same exact idea. So sort of getting back to the question that's been asked, what gets us those gradients, right? Because it seems like kind of a strong assumption that like, okay, you're like relying entirely on these gradients and we haven't specified how we're going to get those. Calculus gives us those. I'm not going to derive this now, but I promise, like, provided we meet certain conditions about how we put together a function, calculus will just give us these for free and it'll be great. As long as, you know, we meet certain conditions in how we structure our landscape. Okay. First of all, also, does the name gradient descent make sense now? Basically, if a gradient is this sort of direction vector, right, then we are slowly descending through this space by following gradients. That's it. Does gradient descent make some sense? There are questions about this before I move on to loss functions. Yeah.
But why do we want to reach the bottom?
Yeah, great question. So that is actually a super good setup question for talking about loss functions, because so far I haven't described why we want to reach the bottom and what that bottom corresponds to. And the whole idea of like structuring that landscape such that coincidentally, the bottom of that landscape corresponds to something that we want to be true about our model. That's the whole purpose of a loss function. So the loss function is going to structure our landscape such that the bottom of that landscape corresponds to some very nice properties about the model and how good the model is at performing its task.
So reaching the bottom is like finding out something about
Reaching the bottom is like finding a set of model parameters such that the model performs the task you asked it to do really well. Have I specified how we're going to do this? No, that's loss function's job. Any other questions? That's a good one. Okay, so with that in mind, let's move on to loss functions. So again, we've given this sort of procedure for navigating this potentially high dimensional landscape. But we haven't talked at all about how we define that landscape or what that corresponds to. So we should do that. So first of all, before we get into the loss part of this, functions, you guys know functions. Functions are great. Like you might remember highlights, like linear functions from like algebra. Algebra, yes. It's been a hot minute for me. But like this kind of function like maps x to y, this is probably like your starter function. Perfectly good function, perfectly good function. We can make this more complicated though, right? Like we can do more complicated things with variables. We can also take in more variables as inputs to a function, right? All of these functions that I've given examples of happen to produce just a single number as an output. There's no reason why that has to be true. But for these examples, I just stopped typing after a certain point. So what is a function as a reminder? So a function is just a mapping of an ordered list of inputs to an ordered list of outputs. You might associate them with equations, and that's not wrong. An equation is a really good way of basically enumerating a function or describing a function. But essentially a function is just this mapping of inputs to outputs, right? You give me a set of, like, you give me an X and I'll tell you what the corresponding Y is. You give me a pair XZ and I'll tell you what the corresponding Y is. So that's a function. How about a loss function though? So a loss function, when we're talking about training a neural network, a loss function is responsible for mapping, again, some ordered list of inputs to a single number, something like these Y's, that represents our current altitude in this sort of space that we've talked about navigating via gradient descent. So this gets back to the question that was asked. Okay, that's all well and good, right? But like these functions that you listed, like those don't seem like okay, we can reach the bottom of this function. So what? Like what is that bias? How does this altitude relate to our neural network actually doing better on the task that we want it to do? So here's the key idea. The loss function is basically responsible for comparing the neural network's current output to what the data says the output should actually be. And a lower value of a loss function signifies a closer match. Does this make sense at a high level as like a goal? I know I'm still missing a ton of details about how this is actually implemented, but essentially, if what this means is like the lower we get with our value of a loss function, the better we are actually modeling the current data and predicting what the output should be given a particular input. So, okay, let's get more specific about how we do this. So, as an example, imagine that we have a neural network that, just a simple neural network that predicts like the temperature of the current day, right? So suppose that we have this neural network. I haven't specified anything about how we structure these things, but a neural network is basically just a function, right? It takes some numerical inputs and it produces some numerical outputs. In this case, this particular neural network, let's say it takes 3 numerical inputs. One, the temperature 3 days ago, the temperature 2 days ago, the temperature 1 day ago, and as its output, it is supposed to produce a prediction for the current day's temperature, right? A loss function would, that we would probably use for training this neural network, takes the output of this neural network, the network's predicted temperature, and it also takes as input the actual temperature that we have from some data, right? So it's not hard to imagine how, like, if we had a data set of a bunch of different temperatures logged over time, we can chop it up into these 4-day windows, right? where each 4-day window is a set of like the 3 preceding days temperatures and the label, if you will, for what the actual, that current day's temperature should be. So this is that sort of what did I do? There we go. So this is where that fourth bit of data, in other words, that actual answer, if you will, gets incorporated. So the loss function is responsible for taking in both the network's prediction and what that prediction should be and comparing those, right? And by comparing, I mean produce a number where the lower that number is, the closer they are to each other. So does this make sense at a high level? I know I still owe you guys a bunch more details, but high level kind of makes sense as motivation. Okay. So what kind of loss function could work for these inputs, right? So far I've just specified, well, technically this is a red box, but like so far it's like a black box, right? Like I haven't told you the details of this. So imagine like, okay, this is my first try at creating a loss function, right? I'm going to look at the absolute value of the difference between the actual temperature and the predicted temperature. And I'm just going to like chop that up into a few different pieces. And based on like how bad that difference is, I'm going to assign different numbers, right? So I'm going to assign like 100 if that difference is really big, bigger than 50, 10 if it's like, between 50 and 0, and 0, the actual temperature minus the predicted temperature is 0. Okay, well, we can all go home now, right? Like we're done. We're not done. So it turns out, so remember how I said, again, this is not a calculus lecture, but because we want to be able to use calculus to get us these gradients, if you've taken calculus, great. You haven't, also great. The thing that you need to know here is that calculus does not like this kind of choppy function. This is sometimes associated with probabilistic, but in the actual term for like what calculus doesn't like about this is discontinuity. Like if you look at basically, like if you contrast this with like our idea of like this smooth landscape that we were navigating in a hike earlier, there is no point in that landscape where like the ground just absolutely drops vertically. Like even if like it's something that we would describe as vertical, it's like it's still got like a smooth change, and it's not quite vertical. These kinds of like changes where like it shifts from 100 to 10 with no in between, calculus doesn't work super well with those. So here's our problem. We need calculus to get us gradients from our function. We're trying to set ourselves up with a function such that, we can just like plug in calculus and we're all good. And calculus doesn't know what to do with a choppy function like this. Okay, so let's take 2 of our function, right? So sort of inspired by this sort of need for a smoother function, we're going to shift our attention over to parabolas. Which you may or may not have seen in math class before. Basically just like, basically it's just like y equals x squared. Like that's the function that we're going to take inspiration from. Well, okay. What kind of function could we define where a lower value of that function corresponds to a better match between the prediction and the actual produced output? One answer that you could give to that is this one. Y equals the actual temperature minus the network's predicted temperature, and then you square that difference. Well, okay, let's think about what this means, right? Well, if the network's predicted temperature is equal to the actual temperature, well, that's 0 squared. That's the lowest point of the parabola, right? If on the other hand, that network's predicted temperature, it's not quite the actual temperature, but it's pretty close, we're going to be somewhere close to here, right? So we'll get a value from our loss function that's a little bit higher. Still not super bad, but as we move further and further away to either side, either too low or too high from what we actually want the network to be predicting, we're going to get a higher and higher value, which basically gives us one version of a landscape, right? So if we think of this as sort of the landscape that our network is trying to navigate, and we want to find the bottom of that landscape, if we can get parameters that over a large amount of data correspond to, on average, the lowest part of that landscape, then we've learned a network that actually learns how to predict the current day's temperature pretty darn well. Does that make sense? Okay. So just as a point of interest, this is an actual loss function that is really widely used. The loss function that I just gave you, it's called least squares. If you're ever, like if you keep like doing some machine learning down the road and you hear the term least squares loss, it's exactly this. It's where you compare the model's output by like subtracting the actual value that it's supposed to predict and squaring it. Perfectly good loss. It's been used for ages. But you might be wondering, like, okay, well, that's all well and good if the kind of thing that we want our neural network to produce is a single number, right? What if we don't want that kind of neural network though, right? There are plenty of other things that we might want a neural network to do that don't correspond to like producing a single number and being done. So let's imagine, so sort of inspired by like it's a bird, it's a plane, it's a generic superhero, because I'm not sure if I'm allowed to finish that sentence the correct way. Imagine that we have like an image classification task, right? Very simple image classification task where the thing we're going to try and do is we are going to try and distinguish whether that image contains an image of a bird, of a plane, or of a superhero. So this, as you can kind of see, right, like this is another perfectly good neural network. Technically, there should be a ton more arrows pointing in, one for each individual pixel value, but I've shortened it to like just pass in this array of pixel values. It's a bunch of inputs, but that's allowed as an input space. Okay, how do we approach creating a loss function for this kind of task? Well, okay, let's see. Okay, so as we're trying to like come up with an idea for how we would structure a loss for this kind of network, imagine that imagine that we've already got a neural network that somehow by magic, like we have pretty good parameters for it, and it is actually pretty good at making this kind of prediction. How would we determine which class our network predicted? Suppose that I feed in an image and our network produces 3 numbers. Which of those numbers corresponds to the class that the network predicted, do you think?
Arbitrary.
Arbitrary is definitely one way that seems pretty appealing if we're struggling to train a neural network from experience. What else might we consider as like a way of picking which output class the neural network selected other than arbitrary?
The lowest loss function value?
Lowest loss function value is definitely what we're going to want for training. But for this, there's actually just like a really simple idea of like, hey, what if we just pick the biggest number? Like, so we're going to suppose this network has been trained. And it produces, at each, like given a particular image, 3 different numbers. And the way we're going to interpret what the neural network is telling us about what it thinks that output is we're just going to see which of those numbers was the biggest, right? So let's say that like our neural network, again, let's assume it's already been trained, produced an output corresponding to bird of like 100 and like negative numbers for the other 2. In that case, that would correspond to our neural network really strongly thinking that this is definitely an image of a bird and not of a plane or superhero. On the other hand, suppose that we had like a neural network that produced maybe like 50 for bird output and like 49 for plane output, maybe like a lower number for superhero. That would correspond to a neural network being like, yeah, I think it's a bird, but it could also be a plane. but it's probably not a superhero, right? So this isn't like a super complicated idea, but basically this idea of looking at how high the different outputs are relative to each other as a sign of like how much the neural network thinks it's like one of those outputs over the other. That's going to be like how we interpret the outputs from this kind of model anyway. So getting back to loss functions, how do we sort of reuse that idea to construct a loss function that plays nicely with this, right? So how do we turn this intuition of like wanting our network to give the highest value, the actual correct output, into a loss function? Okay, so our intuition here, as we're approaching constructing this loss function, is going to be to turn our model's outputs into a probability distribution over the possible output classes, right? So again, I haven't said how to do this yet. We'll get to that. But if we imagine instead of having like some number that's like I don't know, like 100 for, you know, like one of these classes, negative 100 for another one, and like 5 for another. If instead we had like some really high number that's still like a probability, some tiny number that's a probability, and like some medium number that's a probability, that instead gives us something to work with. All of a sudden, that allows us to basically like figure out, okay, like that gives us something we can push down on, basically. We want to push down on the negative probability of the correct class. In other words, we want to push the probability of the correct class up. We just take the negative so that we can still go to the bottom of the hill instead of, you know, the top of one. Okay, and then basically we just penalize any probability that's given to an incorrect class. So okay, first of all, before I get to how we're going to do this, one point that people will often say is like, okay, but why should we create like it feels weird that we would need to turn this into a probability distribution, right? Like if we want, let's say that bird is the actual correct output for a class or for a particular image, couldn't we just try and make the output of bird as big as possible, regardless of the other outputs of the model? That's like one question that I've gotten about this before. And I think that's a decent question, but the problem that like training a model that way will run into is that the model during training will just learn to produce super high numbers for every single output class, right? So there actually does need to be some comparison between these different output classes for how the model, like what numbers the model is producing for each instance. Does that make sense? Like we can't just try and like make these numbers as high as possible. Yeah.
Are you trying to say, what if we feed in an image that's none of those, so we need to take account that that's a possibility?
In this scenario, great question. In this scenario, we are assuming that we are not dealing with noisy data, which we absolutely do have to deal with in real life. But in this, you know, like toy scenario, we're assuming that like each of these 3 images in our, or 3, that would be a small data set. Each of the images in our data set is exactly one of these 3 things. Yeah, so basically the thing that we're trying to avoid is having is basically just encouraging the model to produce giant numbers every single time for each one of these. We want to encourage the model to only produce large numbers for the class it's confident in, given a particular image. Okay, so one, like, especially if you've taken any probability, which again, you don't have to, but especially if you've taken any probability, one word that might be coming to mind right now is normalizing. We do love to do that when we're talking about probability. We want to create a probability distribution out of some non-negative numbers. That's fine. You just normalize them, and beautifully they, you know, like divide them by their sum, and like, well, you've ended up with a distribution where the sum of all these different values adds up to 1. That doesn't work in this case. Because this is a neural network that has parameters moving around via gradient descent, and there is no guarantee that these outputs are non-negative. some of these outputs could absolutely be negative. Okay, well, that makes our lives harder. The exponential function is going to enter and save the day appropriately for a superhero themed problem, which I just realized. Okay, so as a reminder, here's the exponential function. It's probably been a long time since you've seen this. If you've seen it at all, basically the exponential function takes this constant value e. E, I think, is a little bit more than 2. Oh gosh, I should know this. Oh, sure. E is a little bit more than 2. I'm just going to go ahead and say that. The exponential function raises e to whatever your input value is. So e to the x. So this function has some nice properties for us. One of those nice properties, it is never negative. In fact, it is always positive, no matter what number you plug in, as long as it's a real number, no matter if it's tiny, no matter if it's huge, you will end up with a strictly positive number. In fact, if you continue this graph, right, like it will get closer and closer and closer to 0 as you get more and more negative in your input. And it'll get closer and closer to infinity as you get more and more positive in your output, but it'll never actually reach 0 or cross that line. That's super appealing for us because, for one thing, this is a nice smooth function, and calculus does like nice smooth functions. So that's going to set us up well. But for another thing, that gives us a really nice way of mapping potentially like values that could be anywhere on the real line to something that's strictly positive, while also preserving which of those values were the biggest to begin with, right? Because if we think about this contrasted with like the absolute value function, if you have a value that's like -7,000 and a value that's like 1, take the absolute value of those -7,000s, output is going to be way higher, not with the exponential function. If you plug in -7,000 here, you will end up with something really, really tiny. You plug in 1 here, you end up with E, which is bigger than whatever that really tiny thing was. So both of those properties are really appealing for us. So how are we going to use this? Okay, enter the softmax. The softmax is a function that we use all the time in machine learning. If you're wondering, like, why is it called the softmax? What is that? It's basically like taking a maximum over a probability distribution, but doing it in a really soft way where you actually end up with just a probability distribution over those outputs. So what is the softmax? Okay, well, this looks like kind of a lot of math. Let me walk you through it. Basically, what we're going to do is imagine that we have, again, our 3 outputs from this neural network. We are going to feed each of them separately into the exponential function. So basically, this bird output, we are going to feed it into the exponential function, and we now have a value of e to the bird output, right? Whatever that value was. We're going to do that for each of our network's values, and we're going to sum all of those together to get a denominator. What are we going to do with that denominator? Well, we're going to divide each of those individual exponentiated values by that same denominator. So what does this mean? Well, now, instead of having just 3 arbitrary numbers that the neural network spat out for these classes, we have a probability distribution over these classes, where the biggest probability corresponds to the class that the neural network gave the highest output to. It's real convenient for us. As an example, right? So amazing, we've turned an arbitrary list of numbers into a probability distribution. If we have, for example, a case where we've got an array of 6 numbers, right? And we apply the softmax function to it. First of all, here's what the numbers that result from that look like. But there are a few properties that I want to know, right? First of all, the biggest number here in the top row corresponds to the biggest number in the bottom row. And actually, that's even more general. If you look at the ordering of which numbers are biggest to smallest in the top row, that ordering is exactly preserved in the bottom row. However, this is a probability distribution, which means it takes into account, if we have a neural network that is producing massive numbers for all 3 output classes, that's not going to do that neural network any more favors anymore, because we are comparing how that neural network's output for one class differed from the outputs it produced for the other ones. So what are we going to do to turn this into a loss? We're just going to take the negative of the softmax value that corresponds to the actual correct class. That's it. We have a probability, right? Let's say that the actual value for a particular image is bird. We're going to have the model produce a probability for that. We want that probability to be high. So the loss that we're going to define is just the negative of that. So if we can drive the negative probability of the correct class as low as possible, then the lowest that can be is -1, which corresponds to giving probability 1 to that item, right? So that's great. I mean, that's basically our job. As a side note, if we instead like just sandwich a little logarithm function in here, that is the cross entropy loss, which is widely used for training most models, most neural network models these days. The log here isn't actually necessary for like proving that like, you know, this loss would also be perfectly fine to use. It's just that in practice for like numerical stability reasons, the log ends up being helpful for us. But conceptually, this is the same idea as this one. We're just trying to push down the negative probability of the correct class. That makes sense. Okay, cool. So in summary about loss functions. So what does our loss function gives us? What does our loss function give us? There we go. It gives us a landscape, first of all. Okay, what kind of landscape? One where the lower altitude corresponds to doing better on that task, right? Which I think I've convinced you of, right? Like if we have a model that is consistently getting really low scores on our loss function, well, then it's producing outputs that basically match up with what we want the network to produce. The last thing, our loss function, as we've defined them, they happen to be these nice smooth functions that play really nicely with calculus. So that calculus is going to be able to give us those gradients, those sort of direction vectors, such that we can adjust our current location iteratively and work our way to a better set of model parameters. Okay, so I know I've kind of already alluded to this, but let's explicitly do this. Let's put these two ideas together and train a neural network. So if we want to construct and train a neural network, for example, our superhero one. First, I didn't mention this, but collect a lot of labeled training data. So this is not super conceptually interesting to talk about, but oh gosh, in terms of like the actual resources it takes to train a model, this is probably going to be the step that takes the most time. But once you've got your labeled training data, you're going to compose this is for the calculus folks out there, a differentiable function. For the rest, you know, for the non-calculus folks, again, I said that, just a function that has certain nice properties of the input, and insert like plenty of these like blocks of to be learned parameters that you initialize randomly, right? Basically like construct a really complicated function and stuff it full of parameters that we can adjust later. What do we do after that? Okay, we're going to feed the output of that current function, the neural network, paired with the correct answer for that instance into our loss function. And then we're going to ask calculus for the gradient of that loss so that we can keep adjusting those neural network parameters. And we just rinse and repeat between steps 3 and 4 until we are not managing to go any lower on our loss. That is the process of training a neural network in a nutshell. First of all, does that make sense? Okay, so some quick parting words that I should address. One big one that I should mention. First of all, imagine like back to our hiking example. What if the valley that we start in is not the only valley on the map? Imagine that like the valley that we start in is surrounded by like some high mountain ranges, right? I don't know how geography works, I think that's possible. Imagine it's like a crater, right? Just like a big crater where like, no, we're definitely in a bowl. But imagine that there's a deeper crater that's just next door. This procedure is not going to alert us to the existence of that deeper crater, right? We're going to be able to get to the bottom of the one we're currently in, and then we'll think we're done. But actually, somewhere way else on the map, it could be that like, actually, there's a much lower altitude that we could be at. That is a problem with gradient descent. If you hear about people training neural networks, often they will choose different random initializations. In other words, different random starting points to see like, okay, we're going to hedge our bets and just see if one of these does better than the other. We're going to hope that one of them is somewhere around this deeper crater. But this is actually a real problem that like, if you're training neural networks, a ton of time and energy and machine learning research has gone into trying to address this problem in different ways. So that's one thing I should mention. And finally, I want to talk a little bit about like the implications of this training procedure for data, right? Because we think like, especially in sort of the popular imagination, right? When we're thinking of these really famous neural networks, right? Like DALL-E or ChatGPT, we kind of think of them as like storing data from the internet, right? In some way. That's not entirely true. So if we think about what each separate instance of data contributes, it actually contributes just a bunch of little nudges to the model's parameters over the course of training. It's not explicitly stored anywhere. It's not like there's like some database of, you know, like all the models data that the neural network is building up over time. The neural network is just slowly adjusting its parameters to try and model that data really well. That said, so data is not explicitly stored anywhere in the neural network, but if the network is large enough, some of its parameters in order to do well on that loss function might start to encode patterns that correspond to relatively few instances of data. Which is when you start to get outputs from neural networks that, for example, look like almost carbon copies of pieces of training data that it's been fed. So I just wanted to like talk a little bit about that, since like how neural networks encode data is like something that is talked about with like different degrees of success in popular media. So I just wanted to address that. Okay, thanks everyone. I think that's what I planned to talk about. Any questions?
All right. Well, let's think. Oh, did you have did somebody have a question?
Yeah.
So, 2 slides ago, you said that, yeah, here, yeah, it's not the only one. And I think the issue is that, yeah, we don't know the exact whole hypothesis space.
Yeah.
Theoretically, if there was a way of like finding like a function for the whole hypothesis space,
Yeah.
would it be possible to just know it?
Well, okay, so there are a couple of different answers to this question that I want to give. One is if you happen to have a very, some would say carefully, some would say simply structured neural network, and that neural network plus its loss function are convex.
Like SVM?
SVMs are not convex, but logistic regression is, for example. This gets like further into the theory than we need to go, but basically there's a whole bunch of optimization theory on convexity, which basically corresponds to like this high dimensional space is a bowl. The entire thing is a bowl. And if it has that property, then it guarantees that there is a single valley, right? That is not the case for the vast majority of neural networks out there these days. There's a reason why some people refer to like, you know, convex models as like the simpler ones. So that would be one. What's the other thing that I wanted to say? I think that was the main thing. But also, the whole hypothesis space. The other thing that I kind of want to address, and again, this is like this is maybe a little bit more calculus-y than some of the stuff that I've said before, but if we think about like, for those of you who have taken calculus, if we think about how we calculate derivatives or gradients in calculus, right? We tend to, and like if we think about finding the minimum of a function, well, the thing that we usually do is we try and like find these inflection points, right? Or like the gradient is 0 here, so I'm going to like check all of those points, like the minimum will be one of those. For functions as complex as neural networks, we actually need to calculate the gradient in a different way. It is actually not practical for us to store a closed expression for the gradient. So each time we do this, if you've heard the term back propagation before, that basically corresponds to like working our way backwards through the network each and every time in order to figure out what the gradient is. We don't have a closed expression because we couldn't fit it on the machine in most cases. And so therefore, like, yes, in theory, if we had that nice closed expression for that gradient, we could try just like looking for like, where is this zero? In practice, we don't have that closed expression. But, yeah.
How much math? Well, if we were to do research in this, or maybe become a machine learning, I don't know, technician, I don't know.
Yeah.
How much math do you need?
That depends a lot on exactly what you're doing. So if you are, and this varies, so I can speak more knowledgeably about like the research side of this, even within like the set of researchers who work on machine learning or natural language processing, that varies wildly. Some people have a lot of mathematical background and like really enjoy like digging into the optimization functions and, you know, like sort of the more theoretical guarantees about models. Other people these days, actually, there's a whole other sort of branch of research that goes into more like using existing models and trying to characterize something about the data or how those models use data. And that actually is something that lends itself pretty poorly to a purely mathematical way of looking at things. Because it's really like, if we think about all the forms of like, for one thing, societal bias, right? You don't have a mathematical function for that. That's extremely complicated. And so therefore, like, if you are working more with like, just like existing models or like training those models on further data and trying to explore the implications of that data for like what the model is doing, that can actually skew fairly non-mathematical in terms of the research that people typically do. Good question, but it's all over the place. Basically, if you can imagine a research direction, someone's probably working on it, and that research direction may or may not involve a bunch of math. Depends.
All right, I know that we're just a couple minutes over time because you guys had some fantastic questions. Let's give Sophia a round of applause because she did amazing. She will be joining us again on the 26th, same room, same time, 12:30, and giving more of a talk on demystifying ChatGPT and that natural language processing. So hope you guys join us for that. But thank you so much for attending today and enjoy the rest of your day. The sun came out. Welcome spring. So have a great day, everybody.